As we saw earlier, one way to share the high-speed channel among multiple users in a cell is to use TDM. Recall that only one user is served in a 2 millisecond interval with the TDM approach. Assume that 70% of the downlink power is available for the high-speed channel. First, the HSSCCH subframe indicates that the data is for user 1. HSSCCH also provide relevant information on how to interpret and decode the associated HSDSCH. User 1 starts decoding the data transmitted on the HSDSCH using 10 OVSF codes. Now, the HSSCCH subframe indicates that the data is for user 2. User 2 obtains the data from the HSDSCH using 5 OVSF codes. The HSSCCH subframe now specifies that the data is for user 3. User 3 utilizes 15 OVSF codes to obtain the data from the HSDSCH. Another way to share the high-speed channel among multiple users in a cell is to use CDM. Recall that more than one user can be served in a 2 millisecond interval in a CDM approach. Assume that 70% of the downlink power is available for the high-speed data transmission. Remember that one HSSCCH is associated with one HSDSCH. The HSSCCH1 subframe indicates that the data on the HSDSCH1 is for user 1, while the HSSCCH2 subframe indicates that the data on the HSDSCH2 is for user 2. User 1 obtains data using 10 HSPDSCH codes, and user 2 obtains data using 5 HSPDSCH codes. The HSSCCH1 subframe indicates that the data on the HSDSCH1 is for user 1, while the HSSCCH2 subframe indicates that the data on the HSDSCH2 is for user 3. User 1 obtains data using 10 HSPDSCH codes, and user 3 obtains data using 5 HSPDSCH codes. The HSSCCH1 subframe indicates that the data on the HSDSCH1 is for user 1, while the HSSCCH2 subframe indicates that the data on the HSDSCH2 is for user 2. User 1 obtains data using 10 HSPDSCH codes, and user 2 obtains data using 5 HSPDSCH codes. Let's see how the UE obtains data from the HSDSCH. The UE utilizes its identity, called HRNTI, to see if the HSSCCH contains data for it. The node B transmits the packet on the HSDSCH during a 2 millisecond interval. The HSDSCH is received at the UE after the propagation delay. If the UE decodes the packet correctly, it sends an ACK 5 milliseconds after decoding the packet. Otherwise, the UE sends a NAC to the node B. Let's summarize the overall hybrid ARQ operation. The user data is coded using turbo coding, and a packet is formed at the node B. Node B transmits packet P1 on the HSDSCH, and the UE attempts to decode the packet. Since the UE cannot decode the packet correctly, it sends a NAC to the node B on the HSDPCCH. Node B then sends packet P2 that may have a priority of systematic or non-systematic bits. UE combines P2 and P1 to decode the packet. Since the UE decodes the packet correctly, it sends an ACK to the node B on the HSDPCCH. Node B then stops retransmission of the packet. Node B can now transmit a new packet. Let's discuss data rates in an HSDPA system. The chip rate is 3.84 megachips per second. Since the spreading factor of 16 is used, the modulation symbol rate is 3.84 megachips per second divided by 16, which is 240 kilosymbols per second. Recall that the data transmission on the HSDSCH occurs in 2 millisecond subframes. Hence, the number of modulation symbols that can be transmitted in one subframe is 240 kilosymbols per second multiplied by 2 milliseconds, which is 480 modulation symbols. Now the million-dollar question is, how to get a data rate of 14 megabits per second? The standard defines the transport block size to be 27,952 bits. Since one transport block is transmitted in 2 millisecond subframe, the data rate is 27,952 bits divided by 2 milliseconds, which is approximately 14 megabits per second. Now let's calculate the effective coding rate. The effective coding rate is the ratio of the number of information bits and the effective number of turbo code symbols that are transmitted over the air. To find the number of turbo code symbols, let's work backwards. We know that we can transmit 480 modulation symbols using one OVSF code at SF16. Since there are 15 OVSF codes available for the HSDSCH, we can transmit 480 times 15 equals 28,800 modulation symbols. Since turbo coding gives 27,952 times 3 equals 83,856 turbo code symbols, only 28,800 of these symbols can be selected for transmission over the air. The effective coding rate, therefore, is the ratio of 27,952 bits divided by 28,800, which is 0.97.